Okay, hello again, everybody, wherever you're watching this from. We're going to continue now in this lecture talking about aqueous solutions of weak acids and weak bases, as well as a few other items that pertain to pHs of aqueous solutions. So the topic is in your textbook is 6D, and the items that are shown here are the ones that correspond exactly to toolboxes and examples in your text. Yes, you can read all of these yourself in the text to get reinforcement of it, but I think it's a good idea to go over all of these in a little bit of detail so you can see the general approach that's used in solving problems like this that involve pH of acids and bases, and as we'll see, of salt solutions as well. So first thing we're going to do then is to look at one of the toolboxes. As you know, Atkins has guidance for problem solving by having a series of these toolboxes in every one of the chapters. This one is toolbox 6D.1, and it summarizes the overall steps that are used in calculating the pH of a solution of a weak acid. There's another one for calculating pHs of weak bases as well that we'll get to a little later. Now, the conceptual basis is one we've already talked about in class. Because the proton transfer equilibrium is established as soon as a weak acid is dissolved in water, I've mentioned that before, the attainment of equilibrium is almost instantaneous. And so when a weak acid of any kind, say acetic acid or something else, is put in water, the equilibrium is reached almost immediately. And so the procedures that we're going to talk about have to do with assuming that equilibrium has been reached, which it does very quickly. Now, in determining the pH of a solution of a weak acid, unlike a strong acid, where, as we've said, you can assume that in a strong acid, the acid is completely dissociated and the hydronium ion concentration will be whatever the original acid concentration was that was put in. However, as we know, for a weak acid, that's not true. When a weak acid reaches equilibrium in aqueous solution, the concentration of hydronium ions is only a small part of the original amount of the weak acid that went in. And so we have to look at it from the standpoint of an equilibrium problem, which is what this procedure that we're going to talk about covers. Now, the general procedure is one that will come as no surprise. We'll start by writing the equation for the dissociation of the weak acid. We'll have to know the Ka in order to determine the pH. Kas, as we've seen, are tabulated. There's many of them that can be looked up. And these Kas have to do with that proton transfer equilibrium, as your book calls it. So we'll set up an ICE table, like the one down here, which we've used before for other kinds of problems, and look at it from the standpoint of the dissociation of the weak acid. The components involved are the weak acid itself, which is HA, and then the products that result from its ionization in water, hydronium ions, and the conjugate base of the weak acid, which is, in this case, A minus. So the initial concentration then is simply the initial concentration of HA, whatever that may be. And we'll assume that the initial concentrations of hydronium ions and the conjugate base are essentially zero. Now, for the conjugate base, that is exactly true. Of course, for the hydronium ions, the pure water itself has a certain concentration of hydronium ions, which is 10 to the minus 7th molar. So it's not strictly true that the initial concentration of hydronium ion is zero, but for the purposes of the kinds of initial concentrations we'll be talking about, we can assume it to be essentially zero. So in approaching equilibrium, we can pick the easiest way to do this. And so the change in concentration of the original HA, we'll say, is minus X, and the change in concentration of the hydronium ion and the conjugate base are just plus X each. So then at equilibrium, concentration of the acid is the initial concentration minus X, whatever that is, and the concentrations of the hydronium ion and conjugate base are both X. So when this kind of a table is set up, what you'll wind up with, of course, as we'll see, is the equilibrium constant equal to the appropriate concentrations. And because of the two concentrations, the hydronium ion and the conjugate base, as we'll see, you wind up with a quadratic equation. But as we'll see, there is a way to simplify this that works in almost all cases. We'll get to that when we go to one of the actual problems. As a general rule, and this is shown over here, and I'm not going to go through all the verbiage here, but if the numerical value of the initial concentration of HA, whatever that is at least 2 orders of magnitude, that's about a value of 100, times as large as the Ka, then the approximation that we can assume that it's much larger will be valid. I'll show you examples of that when we go through these problems. So once we know what the concentration of the H3O is, H3O plus is, from the equilibrium setup, we can determine the pH easily by taking minus the log of that concentration, which, as we know, is what the pH is all about. So let's look at a specific example that Atkins has. It says example 6D.1, and it involves calculating the pH and percentage deprotonation of a weak acid. All that the deprotonation means is the extent to which the original HA has dissociated into H3O plus and A minus. So the example shown here is, I'm not going to go through all the setup of this. We'll just look at the molecules that are involved and get to the point. An acetic acid solution, this is acetic acid right here, that is originally is 0.08 molar. That's the initial concentration of acetic acid. And the Ka for acetic acid is 1.8 times 10 to the minus 5. So what first all of his examples is to go through this sequence of thoughts: anticipate, plan, evaluate, and so on. The anticipation, of course, for this is that because the solution is that of an acid, we expect the pH to be less than 7. And if you calculate something that's not, you'll know that you made a mistake somewhere. And because the acid is weak, we can expect only a small percentage of deprotonation, on the order of a few percent at most. So the plan, of course, is to use the equilibrium approach that we already talked about. So here is the reaction of interest: acetic acid plus water. They have a typo here. This should be H2O, not H3O, going to hydronium ions plus acetate ions. And the Ka for acetic acid, which can be looked up in a table, is the product of these two concentrations then, hydronium ion and the acetate, divided by the concentration of acetic acid at equilibrium, not the initial concentration. So here's the ice table that results from that. Again, it's just like in that toolbox. The initial concentration of the acetic acid, in this case, is 0.08, and the concentrations of hydronium and acetate are both 0, we'll assume. The change in concentration then of the acetic acid is minus X, and of course for the hydronium ion and acetate are each plus X. So in the equilibrium situation, the concentration of acetic acid will be the initial 0.08 minus X, and the concentrations of H3O and acetate will each be X. So if we set up the simple equilibrium constant expression like up here, it's 1.8 times 10 to the minus 5. That's the numerical value of Ka. And so it should be equal to X times X. Hydronium ion and acetate are both X, so that's just X squared, divided by the initial concentration minus whatever X turns out to be. And so the simplification that we can make at this point involves assuming that X, whatever the extent of reaction was, is very small compared to the initial concentration. We have to verify that at the end, but we can make that assumption, and that simplifies this to an expression like this, so we don't have to use the quadratic formula. If it turns out that X is not negligibly small compared to 0.08, then you have to go through the procedure of using the quadratic formula, coming up with the roots of the equation that way. But for right now, we're going to assume that this assumption is valid, that X is very small compared to 0.08, at least almost 100 times smaller. So we set it up like this, just rearrange this and solve for X, take the square root of this times that, and you get two roots, of course. The negative root has no physical meaning, so we'll just look at the positive root, 1.2 times 10 to the minus 3. So now we know the value of X, of course, is the value of the hydronium ion concentration at equilibrium. So the pH is simply minus the log of that. So here it is. The pH then is minus the log of 1.2 times 10 to the minus 3, which is 2.92. That's a little graphic over here where they show the scale. And as we expected, the pH is less than 7 because it's an acidic solution. Now, the percent deprotonated is simply the concentration of the hydronium ions divided by the initial concentration of the acid. That essentially gives what percent was deprotonated. If this had turned out to be 0, then the percent deprotonation would be 0. In this case, we know that the concentration is 1.2 times 10 to the minus 3. And so we divide that by the initial concentration of 0.08, multiply by 100%, and it turns out to be 1.5%. And so again, in this little graphic over here, they show in a simple figure what percentage of the entire amount is deprotonated, 1.5%, which is very small. So to conclude then, as anticipated, the pH is less than 7, and the percent deprotonated is small. And that's what you would expect to be the case. And the other point that they bring up here, which we're not going to be concerned about, because we're not going to consider situations where it applies. One of the things that we're also assuming in setting all this up is that here's the amount of hydronium ions initially and at equilibrium. Now, if the equilibrium constant is sufficiently small, the concentration of hydronium ions at equilibrium may be very small and not a whole lot larger than the concentration of hydronium ions in pure water, which is 10 to the minus 7. If, for example, this turned out to, if the value of X turned out to be something like 8 times 10 to the minus 7, then in fact, the concentration of hydronium ions that came from the acetic acid is not a whole lot larger than what would be in the water in the first place. And so in that case, this simple approach is not valid. And there's a way to take this into account. But as I said, we're not going to do that. We're going to assume in all cases that we deal with that the hydronium ion concentration from the water itself is negligibly small. I only point this out because in his examples here, he talks about the assumption that the autoprotolysis of water can be ignored is also valid. And he uses that as a criterion that the pH is less than 6. All that means is that if the pH is less than 6, then it means that the concentration of hydronium ions from the acetic acid is more than 10 times larger than it would be from the water itself. But again, we're not going to have to check for this in each case because we're going to assume it's always valid. So that's the approach for going about finding the pH of a weak acid solution, knowing the initial concentration and the Ka. Now, the problem the other way around, which sometimes happens, is knowing the pH and trying to calculate what the Ka value would be given that. So to do that, you need to know the pH and you need to know the initial concentration. Other than that, the approach is very much the same. You set up an ice table to do the same thing, except that you're, instead of looking for the concentration of hydronium ions, which you already know because you know the pH, we're looking for the value of Ka itself. And so this is the other angle on this kind of a problem. So in this particular case, they're saying that the pH of a 0.01 molar aqueous solution of some carboxylic acid, you don't know what it is, because if you did, you could just look up its Ka in a table. The pH of a 0.01 molar solution is 2.95. So you're trying to find out from that information what is the Ka and the pKa, which is just minus the log of the Ka. So again, anticipating, since all carboxylic acids are weak acids, we expect that Ka will be much less than 1. We already saw for acetic acid, for example, it's about 10 to the minus 5, so that's 10,000 times smaller than 1. Now, the plan then, of course, is to use the equilibrium approach, the ice table, to determine what the hydronium ion concentration is from the pH, and then calculate backwards to find the Ka that must give it. So here we are, setting up the equation itself, the reaction itself. Here's the HA. Here's their typo again. This is H2O for water. And it equilibrates to form hydronium ions and acetate ions. And so the equilibrium constant expression, again, just as we saw in the previous problem, is the concentrations of hydronium ion and its conjugate base of the original acid divided by the concentration of the acid itself at equilibrium. Now, one of the things that we're assuming in all of this, of course, is that in getting from the original acid to the equilibrium situation, that the concentrations of all of these things are predictable based on this Ka. As we've already seen, the Ka varies with temperature, and so that's why it's important to know what temperature that the values are correct at. For all of our cases, we'll assume it's 25 degrees. So now, we know the H3O+, and we know that because we know the pH. And so as we've seen before, the hydronium ion concentration is just 10 to the minus pH number, which is 10 to the minus 2.95 from this problem. And so that turns out to be 0.0011 moles per liter. That's the concentration of hydronium ion at equilibrium. So because the hydronium ion concentration is 0.0011, the conjugate base must also have the same concentration because you get one of each when the weak acid dissociates. So when we know one, we know the other. So that's why we can say that the concentration of A minus is the same as the hydronium ion concentration. And so again, the concentration of HA at equilibrium is just the initial concentration minus this concentration of the H3O+, which we now know. So setting this up as before, the equilibrium constant expression right here is just Ka is 0.0011 squared, because both of these two are 0.0011, divided by the 0.01 initial concentration minus that concentration of H3O+ is 1.4 times 10 to the minus 4. So the Ka then turns out to be that. You can see it is a weak acid as expected. It's about 10 times stronger than acetic acid, though, which we've seen has a Ka of about 1.8 times 10 to the minus 5. But it's still a weak acid, as we can see. And so because we know the Ka, the pKa is just minus the log of that, which is minus the log of 1.4 times 10 to the minus 4, which is 3.85. And so it turns out that this particular acid is, well, it says as expected, the Ka is much less than 1. The acid itself is mandelic acid. I'm not going to go through the structure of all this. This C6H5 is a benzene ring that has all of this attached to it. Okay, and here's the carboxylic acid entity, and this is the hydrogen that's being lost right here. It's used as an antiseptic, in fact. It's a mild antiseptic. Anyway, so you can see that both approaches, either knowing the Ka and the initial concentration, or knowing the initial concentration and the pH, in either case, you can interrelate all of these terms, the Ka itself, the pH, and the hydronium ion concentration, as well as the concentration of the conjugate base. So there we are. Now, we can use the same approach, basically, to determine the pH of a solution of a weak base. The situation is a little bit different because the equilibrium is different, but the net result is essentially the same. Here's that toolbox that he's using for that. I'm not going to go through all the details of this. Suffice it to say that in this case, the weak base, B, when it acts as a base, is accepting a proton. And it's accepting a proton from water, of course, to form Hb plus and leave behind OH minus, which originally was part of a water molecule. So other than that, the procedure is much the same. The initial concentration of the base, whatever it is just represented by this. The initial concentrations of the conjugate acid of that base and the conjugate base of water are both 0, we'll assume. So again, using that same procedure, we can just say that the change in concentration of the base is minus X, and the increase in concentration of these two components are both plus X. So at equilibrium, concentration of B is the initial concentration minus X, and the concentration of both Hb plus and OH minus are both X. And so we can use the same approach then to set up the equilibrium constant expression. In this case, it will be a Kb rather than a Ka. And what we're going to get is not the hydronium ion concentration, but the hydroxide concentration. But knowing the hydroxide concentration, we can easily determine the hydronium ion concentration by knowing Kw. And so we'll see that in an example that we'll do right now. So here's an example of, from the book of calculating the pH and the percent protonation, a weak base. I'll go back here in my setup here, which is in the lecture notes. I had a bit of a typo here when I said calculating the percent deprotonation of a weak base. It's actually the percent protonation because it acquires a proton. So here we are. Here's the reaction itself. Now they got the formula for water correct. So the water reacts with, in this case, the weak base is methylamine. Methylamine is simply an ammonia molecule that has a methyl group in place of one of the hydrogens. And so its behavior is much the same as ammonia. The nitrogen has a lone pair in both ammonia and in methylamine, so they behave chemically very similarly. But this is the overall equilibration. It forms then methylammonium ion, which is analogous to the ammonium ion from ammonia, and hydroxide. Okay. Now, in this case, you're told that the initial concentration of the methylamine was 0.2 molar, and that the Kb for methylamine is 3.6 times 10 to the minus 4. So that's exactly analogous to the information we had when we determined the pH of a weak acid. So again, here's the equilibrium table that's set up. The initial concentration of methylamine is 0.2 molar. Methylammonium and hydroxide are both 0. The methylamine goes down by X. The methylammonium ion and hydroxide go up by X. So at equilibrium, concentration of methylamine is 0.2 minus X, and both of these two are X. And so the expression you wind up with is exactly analogous to what we saw for the weak acid, except now it's a Kb, which is equal to X squared, because both of these are equal to X. So it's X squared over 0.2 minus X, which is this value here. And so again, we will make the assumption that X in this case is very small compared to 0.2 and can be neglected. So we simplify it to an expression like that. So now, just by rearranging and taking the square root of 0.2 times 3.6 times 10 to the minus 4, we get 8.5 times 10 to the minus 3. And again, only the positive root has a physical meaning. So now, what does that correspond to, though? It's not the concentration of hydronium ion, it's the concentration of hydroxide ion, all right? So there are two ways you can go about this. You can either, from this number, calculate directly what is the hydronium ion concentration, and you can get that by dividing 1 times 10 to the minus 14, which is the Kw for water, by 8.5 times 10 to the minus 3. That will give you the hydronium ion concentration. Or you can do as Atkins does here, is use this value to determine a pOH, which is just minus the log of that number. So the pOH then is minus the log of 8.5 times 10 to the minus 3, which is 2.07. Now, that's the pOH, but we know that the sum of the pH and the pOH has to be 14. So in this case, the pH then is just 14 minus 2.07, or 11.93. And so indeed, we see that the pH is well above 7. It's a basic solution as we'd expect. And so in this case, it's up here somewhere on this little graphic. Now, the percent protonation, just like we did for the weak acid, is now the initial concentration divided into the concentration of the OH minus at equilibrium, which is 8.5 times 10 to the minus 3 times 100% is 4.2%. And so the percent protonation is quite small. It's less than 5%, which is usually a good indication that this simplification up here is a valid one. Okay. So again, evaluating as anticipated, the pH is greater than 7, and the percent protonated is quite small, because 8.5 times 10 to the minus 3 is the value that it has. It is in the value. The assumption that it's much less than 0.2 is valid, the valid one. So those are the approaches to determining the pH of solutions that are either a weak acid or a weak base, as well as determining the extent of deprotonation or protonation. So we've essentially covered all of these examples from the textbook, the two toolboxes and 3 examples. All right. Now, we're going to look at another aspect of this that at first is not immediately obvious, but as you'll see in a few minutes, it follows directly from the equilibrium we've been talking about. It turns out that because a weak acid has a conjugate base, and when a weak acid deprotonates an aqueous solution, it forms a hydronium ion and its conjugate base. Now, suppose that you make a solution that starts with the weak base, does not contain any of the weak acid that it could be derived from, and make a solution that contains the A minus, but does not contain any HA. Well, because that A minus is the conjugate base of a weak acid, it in fact will behave like a base. It will accept a proton. And in doing so, it actually forms its conjugate acid, which is the HA we've been talking about. This may seem a little convoluted at first, but you'll see what I mean in a few minutes when we talk about some of these things. Now, the basis of all of this is tabulated here. These are two tables from your book. These are all cations, and just a few cations, a handful of cations in water. And what they're showing here is that these cations, some of them, behave like a weak acid. They have a Ka, all right, and hence a pKa. So that's what we're going to go through here now for a few minutes. Let's look first at, they divide these cations into three types: acidic ones, neutral ones, and basic ones. These are simply ones that behave like a base and ones that behave like an acid. And these neutral ones, which we'll look at first, are ones that behave as neither. And the reason for that is based on what we talked about in the last lecture. The cations of the alkali metals, which are these, the alkaline earth metals and silver and a few others, are essentially the conjugate base the conjugate acid of a very strong base: lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on. As the conjugate acids of very strong bases, they are very, very weak acids. And in fact, they do not even behave as an acid. In other words, they will not donate a proton. They have no protons to donate, of course, but they have essentially no acidic properties at all. And so for that reason, they're called neutral. They don't affect the pH, the concentration of either hydronium ions or hydroxide ions in solution. Now, ones that behave like acids are summarized here. And these are just a small handful, and we'll just look at a couple that we're familiar with. The ammonium ion, for example. The ammonium ion is the conjugate acid of a weak base. The weak base is ammonia, as we've just seen. And the ammonium ion is its conjugate acid. As an acid, it has its own Ka. Now, this Ka is related to the Kb of ammonia, as we'll see when we go through a couple of problems about this. But the fact is that all of these bases, and these are all ones that contain nitrogen. And nitrogen always has a lone pair, and all nitrogen-containing ions behave essentially the same because of that lone pair. But anyway, you can see that, for example, the ammonium ion has a Kb of 10 to the minus 10. Some of these are stronger than that. They're 4 or 5 orders of magnitude stronger. Still weak, but much stronger than the ammonium ion, for example. In any case, all of these behave like weak acids. They are the conjugate acid of a weak base. We just saw the case for methylammonium ion, which is the conjugate acid of methylamine. And of course, it's very similar to ammonia itself, and that's why these two values are very close together here. But now, another type of cation that behaves like a weak acid is one that we talked a little bit about last semester when we talked about complex ions. And these are less obvious. And so I'll just say a few words about them. What they're referred to is small, highly charged metal cations. The iron 3 ion, chromium 3 ion, aluminum 3 ion, and so on. All of these, because they have a large charge, meaning more than 1 or 2, they tend to be small. As you know, the more electrons that are removed, the smaller the species gets. And so, as we talked about last semester, iron 3 or chromium 3 or aluminum 3 do not exist in solution all by themselves. They always are surrounded by this coordination sphere of water molecules, most often 6, so it forms an octahedral complex, as you remember. Sometimes 4, which form either a tetrahedral or a square planar complex, but they're all surrounded in a complex ion by this coordination sphere of water molecules. So when they refer to this as iron 3 as, remember this, hexa aqua iron 3, which is the name of that complex ion. The iron 3 is where the action is. And because of that, this material can behave as a weak acid. And as a weak acid, it can donate a proton. Well, where does the proton come from? Well, it comes from one of these water molecules. There's 6 water molecules here. One of them will lose a proton, okay? And that decreases the charge on the whole species to 2+ and gives up an H3O+, okay? So in essence, one of these water molecules donates a proton to a water molecule that's in solution. that's they're not complex to iron, and it leads to FeH2O taken H2O taken 5 times OH to the 2 plus power, or 2 plus charge. Okay, and so as a result, they behave as weak acids, and you can see that their Kas are on the same order of magnitude as acetic acid, for example. Here's one that's the hexa-aqua aluminum ion, complex ion, has a Ka that's almost the same as acetic acid, which is 1.8 times 10 to the minus 5, you may remember. So these are ones that you may not immediately suspect because they're not quite as obvious as the behavior here for when something is the conjugate acid or weak base. Nevertheless, they behave as weak acids. Now, the last category are ones that have basic properties, and there are essentially none. The reason for that, if you think about it, is because in order to behave as a base, what does the cat, and these are all cations, remember, if they existed, what does a cation have to do to behave like a weak acid? Well, it has to donate a proton. Well, since these things are already have a positive charge because they're cations, they're much less likely to donate another proton and acquire another negative charge. And so as a result, essentially no materials behave that way. Conjugate bases of weak acids don't behave like acids at all. And there are essentially none of them that exist. So this is the categorization of these things that we're going to be talking about now. Now, the other group are anions. All of these are anions in water, and they also can display acidic and basic character. As an anion, of course, they already have a negative charge. So if we look at ones that are neutral first, again, there's a good reason for this because these are ones that are very commonly encountered. These are conjugate bases of strong acids, very strong acids. Chloride is the conjugate base of hydrochloric acid, hydrobromic acid, hydroiodic acid. Nitrate is the conjugate base of nitric acid. Perchlorate is the conjugate base of perchloric acid. All of these are strong acids. They dissociate completely in water. And as we saw last time, the basic properties of the conjugate bases of strong acids are so weak that they have no basic properties at all. In other words, none of them are inclined to accept a proton. Because, for example, if the chloride ion accepted a proton from a water molecule, what does it form? Well, it forms a molecule of HCl, which would immediately dissociate back to H3O plus and chloride. And so as a result, none of these things behave as conjugate bases, or they behave as bases at all. And so as a result, they're referred to as neutral. They don't affect the pH one way or the other. Now, conjugate bases of weak acids. All right, there's a bunch of these. This is where most of them are. These are ones that have basic properties because they're the conjugate base of weak acids. For example, fluoride. Fluoride is the conjugate base of HF, hydrofluoric acid, which is a weak acid. OH minus, of course, is the conjugate base of water. Cyanide ion is the conjugate base of HCN, hydrocyanic acid. Carbonate ion is the conjugate base of carbonic acid, and so on. So all of these behave like bases. They're all negatively charged. They can all accept the proton, which they're quite willing to do, of course, because they have negative charges, all of them. And so as a result, any of these can react with water. They'll be weak bases, but they're still bases. And they will form something that has one fewer negative charge. And we'll look at an example of that. And then finally, the acidic group. There's very few of these for the same reason that there are essentially no basic cations. There are no acidic anions. And the reason, of course, is that when something is an anion and it's supposed to behave like a base, it has to accept another proton. And well, all of these things are these common anions. Very few of them behave as an acid because they're not as inclined to donate another proton, because then they would have a one more negative charge, for the same reason that something that already had a positive charge is not likely to donate or accept another positive charge. So there are very few of these. The ones that are ones that are conjugate bases of a polyprotic acid, which we'll talk about in a future lecture. For example, HSO4 minus is the conjugate base of sulfuric acid, H2SO4. H2SO4 in water dissociates completely to form hydronium ions, and HSO4 minus. That's a strong acid. The HSO4 minus ion is not a strong acid. It's a weak acid, but not terribly weak, as we'll see. H2PO4, dihydrogen phosphate ion, is the conjugate base of phosphoric acid, which is H3PO4. H3PO4 can, in principle, lose up to 3 protons. This is what's left after it loses the first one. So again, it's not likely to act as a base because it already has a negative charge here. So having said all that, what we're going to do then is to look at the 2 other examples that are taken from your textbook. One involves calculating the pH of a salt solution with an acidic cation. That's one of these up here. And the pH of a salt solution with a basic anion, one of these, mainly chosen from down here. Now, if we look back at this figure that followed from the last thing we talked about, these are 4 solutions here that have what's called a universal indicator in them. You may remember in the lab, when you still had labs, that in the lab, we had this pH test paper where it has a chemical, actually several chemicals in it, that will change to different colors depending on the pH. And it's a way of getting within plus or minus a half a pH unit with those papers. Well, you can do the same thing in solution. Put a few drops of that universal indicator in here in a solution. And the color of the solution will tell you about what the pH is. So the 4 solutions that are shown here, and I'm going to make this smaller so we can see the bottom part here. All right. The 4 solutions that are here are pure water, which of course has a pH of 7, and an acetic acid solution. This is a weak acid that we've already talked about. It has whatever the concentration is, it has a pH of 4. So it's a mildly acidic solution. These other 2 solutions are examples of these transition metal cations in solution. Well, they're not both transition metals because one of them is aluminum. But in this first case, this is a solution of aluminum sulfate. Now, sulfate does not affect the pH. It's essentially a neutral anion. But aluminum, the aluminum plus 3 ions, act as weak acids because what's actually involved is the hexa-aqua aluminum 3 ion that we just looked at in that previous table. And so that hexa-aqua aluminum 3 ion can behave as a weak acid, and in solution, that's why this thing looks like it has a pH that's less than 7. It behaves like a mildly acidic solution. The same thing is true for a solution of titanium sulfate. This contains titanium 3 ions, which behave the same way. It's hexa-aqua titanium 3, and it also behaves like a weak acid. It's the conjugate. It's not a conjugate acid of anything. It happens to be one of these complex ions. And so you can see from this pH here that it also behaves like a mildly weak acid. Just to give you an indication, all 3 of these solutions are 0.1 molar. This is 0.1 molar acetic acid, and these are both 0.1 molar in that salt solution, just to give you an approximate comparison. So what it means is that both of these, although they are mildly acidic, are not even as strong an acid as acetic acid, which has a lower pH than both of them do. So these are the solutions that we're going to consider some examples of from your textbook. This is example 6D.4. This is calculating the pH of a salt solution that has an acidic cation. So we expect the solution to behave like a weak acid, and the material that is going to be involved in it is one of these conjugate acids of a weak base. So, and you can read the language up here about where all this comes from. Actually, it's kind of apropos for the current environment we're working in. You're working in the emergency room of a hospital where a patient suffering from influenza has developed metabolic alkalosis. That's a condition in which the pH of the blood is too high. That's why it's called alkalosis instead of acidosis, which would be pH that's too low. Well, among the things that can cause that to happen, of course, is an acidification of the blood from things that you breathe. So what you're told is you have available a stock solution of ammonium chloride, okay, NH4Cl. And what you're trying to determine is what the pH, you have to determine the pH of that ammonium chloride solution so you know how much to administer. Right? So the stock solution that you have available is 0.15 molar in ammonium chloride. Remember, chloride is a neutral anion, as said here, so it shouldn't affect the pH. Ammonium ion is the conjugate acid of ammonia. It behaves like a weak acid, and so you expect the pH to be less than 7. How much less, you don't know until you do a calculation like we're going to do here in a minute. So you can approach this exactly the same way that we did for a weak acid that was intact, the acetic acid, let's say. Treat the solution as that of a weak acid using an equilibrium table, just like we talked about before. So the reaction involved then for the ammonium ion is this one. Here's the ammonium ion, and unlike the case with ammonia giving ammonium ion, the ammonium ion here does not come from ammonia. It comes from a separate solution that contains ammonium ions to begin with, okay? And in fact, it contains ammonium chloride, as we just said. So the ammonium ion reacts with water to form hydronium ions and conjugate base of ammonium, which is ammonia. And of course, hydronium ion is the conjugate acid of water. So because ammonium ion is behaving like an acid, it's a Ka that we need for it, not a Kb. And the equilibrium constant expression will simply be the hydronium ion concentration times the ammonia concentration divided by the ammonium concentration right here. So the setup is similar to what we've already seen. But as we'll see, there's a little twist at the end because you can't find a value for Ka for an ammonium ion. Now, what we need, of course, as I just said, you can look for the Ka of ammonium ion and you won't find it anywhere. And the reason is because the Ka of ammonium ion and the Kb of ammonia, which is tabulated, are related to each other. And they're related because you know that the combination of the two has to be Kw, all right? In other words, the Ka of ammonium is Kw, which is 10 to the minus 14, divided by the Kb of ammonia, the conjugate base of ammonium. I know there's a lot of syllables here and things to keep track of, but do a few of these problems and you'll get the hang of it. So here's the equilibrium table. The ammonium ion initial concentration is 0.15. The hydronium and ammonia concentrations are both 0 initially. The changes again are minus X, plus X, plus X. And so the concentration of ammonium ions at equilibrium is 0.15 minus X, and the H3O plus and ammonia are both X each. So from what I just said, the equilibrium constant expression here, the Ka is given by Kw over the Kb of ammonia, okay? And so it turns out that the Ka then for ammonium ion is 1 times 10 to the minus 14, that's Kw. And this is the Kb of ammonia, 1.8 times 10 to the minus 5. And so the Ka of ammonium is 5.5 times 10 to the minus 10. Now, as I said, you won't find that value in any tables anywhere because it can be easily calculated, as we just did here, by using the Kb of the neutral molecule, ammonia. That's usually how the Kas and Kbs are tabulated. So now we've got our Ka. So if we just put the values, the appropriate values into the equilibrium constant expression here, we've got X times X again, which is X squared, over 0.15 minus X. Again, we'll assume that X is small compared to 0.15, so we can simplify it like this. So just rearrange this, take the square root, and you wind up with 9 times 10 to the minus 6. So that's the concentration of H3O plus, the hydronium ions. So because that X is equal to the hydronium ion concentration, we know that the pH of the solution then should be minus the log of that concentration, which is minus the log of 9.1 times 10 to the minus 6, which is 5.04. Now, that's an acidic solution, all right. It's a mildly acidic solution, but if you look back here, what we just looked at, it's comparable to one of these transition metal ion or highly charged metal ion solutions, the complex ions. It's in that same ballpark, which were on the order of 5, 5.5, or something like that. And so the value we got here is on the order of 5, and the concentration is it's a little less than 0.1, of course. The initial concentration, it's a little bit more, it's about 0.15. But you can see that the acid strength of ammonium is roughly comparable to things like these complex ions that contain transition metals in most cases. So evaluating, as anticipated, the pH is less than 7, so it is basic as we expected. And the approximation that X is less than 5% of 0.15 is valid. In fact, it's valid by a lot. Remember, this was 0.15. X turned out to be about 5 orders of magnitude lower than that. So clearly, X is very, very small compared to 1.15, and so it was a valid assumption. So for our last problem, we'll look at the same thing, but for a basic anion instead of an acidic cation, calculating the pH of a salt solution with a basic anion, excuse me. Calcium acetate. Again, there's some verbiage here. It seems to like medical applications. Calcium acetate is used to treat patients with a kidney disease that results in high levels of phosphate ions in the blood. Calcium binds to the phosphates, makes calcium phosphate instead, which is insoluble, and so it comes out. They say excreted. And so if you're using calcium acetate for this purpose, it's important to know the pH of the solution to avoid complications of the treatment. So that's the background for it. So what we have is a 0.15 molar solution of calcium acetate, and we're trying to find the pH of it. So we can approach it the same way as we just did for the conjugate acid of a weak base. In this case, acetate is the conjugate base of a weak acid, acetic acid. So we anticipate that the acetate ion, since it is the conjugate base of a weak acid, so it should behave like a base, and you should expect the pH to be greater than 7. Right? Calcium acetate is soluble, as essentially all acetates are soluble. That's why it's a popular anion to use when you want to get something in solution. So the plan is the same as we've just done. In this case, when we set up the reaction and the equilibrium table, what we're going to be determining initially is the OH minus concentration, not the hydronium, just like we saw for the weak base that came with acetic acid. So here's the transfer equilibrium for the acetate. Here's water. Here's the acetate ion. And here's the equilibration produces acetic acid and hydroxide ions. All right. And so the expression for this involves a Kb, because acetate is acting like a weak base. Okay. And the Kb then is the acetic acid concentration times the hydroxide, which we'll assume are equal to each other, just like we did before, divided by the concentration of acetate ion at equilibrium. So the initial concentration of the acetate, as we're told, is 2 times 0.15 molar, because there's 2 of them, remember. Go back here, this is so you don't get fooled by this. The calcium acetate, it says, is 0.15 molar. In a solution, remember, there's 2 acetates for every calcium. So the calcium ion concentration in solution is 0.15, but the acetate concentration is 0.30, 2 times that. So that's the situation down here. And so that's why it says here the initial concentration of acetate is 2 times 0.15, which is 0.3 moles per liter. Now, the approach to this, of course, is analogous to what we just did for the ammonium ion. You will not find a Kb for acetate tabulated anywhere because it's a charged ion. What you will find, of course, is a Ka for its conjugate acid, acetic acid. So what you need to do is to look up the Ka for acetic acid, just as we did for the preceding problem, divide it into Kw. Now you'll know what the Kb is for acetate. So that's the plan of action here. So here's the equilibrium table. The initial concentration of acetate is 0.3. Acetic acid and hydroxide are both 0. Changes again are minus X, plus X, and plus X. So at equilibrium, the concentration of acetate is 0.3 minus X. The acetic acid and hydroxide are both X. So we have to determine Kb. Well, here it is. Kb is Kw over the Ka of acetic acid, which is 10 to the minus 14 again, over 1.8 times 10 to the minus 5. Notice that number popping up because we're always using acetic acid and ammonia for a lot of examples, and they have the same numerical value for their Ka and their Kb. And so the Kb is now 5.5 times 10 to the minus 10, which was the same as the Ka for ammonium ion, remember. All right, not to confuse you any further. So now if we just substitute the values that we have here from the equilibrium table, the Kb then is X squared over 0.3 minus X. make this approximation again that the x can be ignored. And if you set it up and rearrange, take the square root, the x, which is now the OH minus concentration, as well as acetic acid, but it's the OH minus concentration, not the hydronium ion, is 1.3 times 10 to the minus 5. So now we can get the POH by taking minus the log of that number, which is what's done here, minus the log of that hydroxide, is 4.89. Now we know the POH, the pH is 14 minus that. That's this last step down here. So it turns out to be 9.1, which is indeed higher than 7. So it's a basic solution as we expected, because the assumption that x is much less than 0.3 is valid, because x turns out to be only 1.3 times 10 to the minus 5. So it's 3 orders of magnitude, 4 orders of magnitude less. So all of this is an approach. There's a lot of numbers here and a lot of setups that we use, but you'll notice they're all basically the same thing. The equilibrium table is very similar for all of them, and the approach is very much the same, especially for simple monoprotic acids and monoprotic bases like this. The equilibrium table is particularly simple because it always involves just one x instead of 2 or 1 and 2 or something like that. So these examples from the book are all fairly simple, but they're very representative of how a lot of these kinds of problems are done. And so there are some homework problems assigned that have the same kind of calculations in it. And after you do several of them, you'll get used to handling all of these kinds of problems to determine these pHs. So we'll continue with more of this kind of subject matter next time. Bye.